Thank you, Michael and Joy, for being here. Also, thank you to my colleague Sergio. My name is Paco Romero, and I'm working in the FI-WARE project. I'm in charge of the integration of Cosmos, which is the GE implementation of the Big Data GE in the data context chapter. So let's start with the presentation. I will do, I think, a short presentation. It will take, I think, half an hour, and then I will do a very simple demo about Cosmos and how you can use it. So let's start with the presentation. What happens? I can move the presentation. I don't know why. Okay, we will do it by hand. This is the index of the presentation. First of all, I will do a very brief introduction to the big data world and the challenges we must afford. Then I will explain the basic concepts that are around the big data area. Then I will explain very quickly what is Cosmos, and I will try to explain the Cosmos architecture and how Cosmos fits in the FI-WARE environment, the FI-WARE ecosystem, and finally I will perform the demo that I was telling you. So now it works. So let's go with the introduction. First of all, the first question when you talk about big data is to ask about how much data is there in the internet, in the enterprises. Well, I found this little joke in the internet when I was finding for some data, some information regarding how much data is there, and I found this news in several blogs or digital papers, talking about which is the new measurement that we are going to use for measuring the data that is there. No? And I found an article from 2008 that was talking about the petabyte age, but then I found another one from July 2012 talking about the exabyte revolution, another one from Cisco talking about the zettabyte area, and finally I found this other article that was talking about we have actually almost no words for describing how much data is there. I think the biggest measure I have found is the yottabyte. I think it's a very big number. So the conclusion is that there is a lot of data in the internet, in enterprises, in the databases, in all our repositories. I finally found a serious article, a serious paper talking about the data growing forecast. This study is for the internet data and is made by Cisco. It was released in May of the current year, and well, among all the data all the information that is described in the slide, the important thing is that in 2017 it is estimated that will be 1.4 zettabytes of data in the internet. It's a quite big volume of information, even if we have in mind that in the last year we have 523 exabytes. That is much less than 1.4 zettabytes. Okay, but this is a study regarding the internet data. But what about the data that is not in the internet? The data that is in the enterprises, in the private intranets, private databases. There is no forecast for this. There is no current studies, and there is no forecast for this data. So the idea, behind this slide is that there is no way to measure this data, and there is much more data than we can imagine. So the next question, well, we have wondered about how much data is there. The next question is: are we ready for this data? Are we ready for processing this data, analyzing this data, even storing this data and managing this data? Well, there are. I have put a couple of traditional large-scale computation systems that you will aware of them. First of all is the data warehousing, and the other one is the CPU bounds. The data warehousing is suitable for the big amount of data that we have today in the internet and in the private networks. Well, having so much data, I think that, for example, copy such vast amount of data to a centralized database is not feasible at all, because we will need a very huge storing capabilities, and we will also not also the storing capabilities, but also a very huge, a very big maintaining capabilities for this data. Even the sources of this data will be very different. This is something that we have to have in mind. We are dealing with databases. The data is very structured. The data is in a single format, but with data from all the internet, from all the databases that we can manage, we have to have in mind that the data will be in various formats, in any language, in any format, in any. Okay. Then we have the timing problems, because having all the data in a centralized place has problem when accessing it, processing it, or even just showing the results of the analysis. Okay, sampling is not a solution, because in the end what we want to have is analysis on all the data, not a sample data. Okay. On the other hand, we have the CPU bounds. And CPU bounds is an effort to distribute the processing capabilities over the data. I think the most known project is the SETI at Home project, that tries to search for intelligence. For intelligence messages in the radio waves that are crossing the universe. And well, the SETI at Home project, what it's doing is just putting these computation capabilities in a lot of computers all over the world, and just performing a very little processing on a very little piece of this information. The problem with projects of this kind is that they are difficult to program, and the most important, they have synchronization issues. We have to wonder what happens if a node fails. What happens with this piece of data that this node was processing? Is it lost? Can we reprogram another computer to deal with this piece of data? How is the communication among nodes if we want to perform this kind of intelligence between nodes? This is something that is really not solved with this kind of project. So we need something more complex. Okay. So the conclusion is that is arising a new paradigm. This is the big data paradigm. Okay, and the big data has new challenges. Okay. It's very common to say that big data spans four dimensions. Some authors say that they span 3 dimensions, but I've put here the 4 dimensions that are volume, velocity, variety, and veracity. The volume, I think there is nothing more to say. We have talked already about the big amount of data that we have today in the internet and in the private companies. But we can say something about the velocity. Okay, the velocity regards about how fast are we able to process the data that we have. Let's think as I say there in the slide, let's think in a fraud detection scenario where we want to know which clients are doing fraud against our company. If we perform such kind of analysis, we can wait for days or even weeks. We need a result in the worst case in hours. So we have to deal with the velocity of the analysis. Okay. Again, we have to deal with the variety of the data. As I told you before, we have to deal with type that is in any format, in any language, any kind of data regarding any kind of area of field. We can have data coming from user, but also data coming from the network, the computer, data coming from the business unit of our company, and we have to deal with this heterogeneous kind of data and merge them in order to have a unique analysis. Okay, and finally the veracity of the data. Because well, I have not put it in the slide, but I found a study that said that I thought I'm talking by memory. 90% of the companies don't trust their own data and their own analysis over the data. And this is a problem because we have a lot of information. We are doing a very big effort to analyze this data, and in the end, we don't trust this data because I guess because the analysis that we are performing on this data are not as good as we need, and finally, the analysis that we are performing are not valid. Okay. The big data presents new challenges. Okay. You have a list there, but we can comment very briefly. First of all, the data has not to be copied to a single location. The data should remain where it is, or in the worst case, the places where the data is stored should enable some kind of sharing mechanism in order to share this information. Another challenge to the big data paradigm is that we have to support the failure of a node. I mean, if an analyzing machine crashes, then the whole analysis must not be affected. And in this sense, we have to enable mechanisms in order to reprogram analysis over pieces of code that were assigned to a certain machine that has crashed. Okay. Anyway, crashes rate should be low in such a system. Okay. Even if we have implemented mechanisms to recover for failures, we should implement a mechanism that is robust. Okay. And finally, we have the scalability challenge in the sense that we have now a lot of data, but in the future we will have more data than the current data. We have seen the forecast and that we manage. So the systems we create must be ready to scale, must be ready to add new computation capabilities, new storing capabilities, new. In the end, it must be scalable because we don't want to have an obsolete big data platform in a couple of years. So, having this new paradigm, it is easy to think that new paradigms will require new technologies. So, which are these new technologies? Okay, this new technology will be explained in this chapter, the basic concepts that are around the big data paradigm. First of all, the MapReduce. MapReduce concept. Which is the MapReduce concept? Okay, this is something that was introduced by Google some years ago. They have a patent on an implementation that they did on this concept, but they did not patent the concept. Okay, they patented an implementation, and so we have nowadays commercial and open source implementation of this concept. We will see that later. But focusing on the concept of the MapReduce, okay, it is based on analyzing the data in a cluster of commodity hardware. So you can think, okay, this is quite similar to the CPU bounds that you have told me before. It's similar, but there is a main and critical difference. And the difference is that all the nodes, not all the nodes in the cluster that we are going to run the MapReduce concept have the same role. Okay. Even within a node, there will be different tasks that will be playing different roles. Okay. This MapReduce concept is something that is task-oriented. Okay, it is not node-oriented. Okay, and the tasks, these tasks that are running in a lot of nodes within the cluster will be orchestrated by a special task. So the first thing that we have to have in mind is that there will be several tasks and running in several nodes, and all these tasks will be playing different roles. So this is quite different to the CPU bounds that we have been talking before. Okay. The second that we have to have in mind is that how this works. Okay. Okay. The way MapReduce works is that first of all, by supposing that the data is accessible to all the nodes and all the tasks within the cluster. Okay. We will talk in the next slide about how this data is available to all the nodes and all the tasks. But for now, we will suppose that this is possible. Okay. Well, all the data, all the big data that we are going to analyze is split into several services, into several pieces. Okay. Each piece of data then is processed by a task, by a single task. Okay, that will run in a node within the cluster. Okay, and it's very important to have in mind that all the processing tasks within the cluster will run the same operation over all the data. Okay, this is called and this task will be called the mappers. Right? Okay, this is the map part of the MapReduce concept. So until now we have a lot of tasks running the same operation over a lot of pieces that come from the data. Well, at the end there will be another kind of task that will be running in a special function that will be to join all the results that the mappers are creating, and their goal is to join all these results and provide this join to the user as the final result of the MapReduce mechanism. These tasks are called the reducers. Okay, and this is the other part of the MapReduce concept. We can see an example here in this slide about how the MapReduce concept works. Okay, let's imagine that we have a file that has these words. Okay, D, driver, car, driver, etc. Okay, and we want to count the occurrences of each one of these words. Well, we will have a master node that is running the orchestration role. Okay, this master node is in charge of splitting the data, passing the data pointers to the different mappers. Okay, is in charge of providing the map implementation and the reduce implementation that we are going to perform within all the tasks. Okay, and is in charge of instantiating this task. So we have in this cluster, for example, we have 4 nodes. Okay, these are the nodes, the dark squares. Okay, and within each node we are running several tasks. Okay, well, everything starts with, as I told you, with the data file. Okay. I'm going to suppose that this is a big data file. Everything starts with this data file being split in several pieces. Okay, this piece of data is sent to this node. This piece of data is sent to this other node, and this piece of data is sent to this other node. Once the pieces of data have been received, we start the mapping task. And what we do in this example is just to map each word with with a count of 1. Okay. Then these maps are sent to the tasks to the reduced task, and the reduced task what performed is, okay, I'm receiving all the counts for each single word, and what I'm going to do is to join these counts into a single count. In this case, what the reducing task receive are for each word a single count. This task simply perform a sum. Okay, they add all the results and provide the final count of all the words that were in the original file. So this is a typical example that you can find in the internet in the documentation about the MapReduce concept. Okay. The other important concept that is around the big data paradigm are the distributed file systems. This is the way that all the data is available to all the nodes and all the tasks. Okay, by using these special file systems. Distributed file systems are based on other nodes that whose purpose is just to store the data, okay? And the way the big data files are stored within this distributed file system is by having a special task owning the files, and this task is in charge of everything that is related to file creation, file deletion, file naming, etc. This task, this daemon, what has is a list of all the files that are in the distributed file system, and for each file, what this task owns is a list of all the data blocks that are composing this file. Data blocks are distributed all over the data nodes, okay? And the task in charge of the file system has a list saying, okay, this file points to these data blocks, okay? The way the data recoverability is ensured is by replicating the different blocks that compose each file. Okay, well, what we are doing is to replicate these blocks on all not on all the nodes, but in a certain number of nodes. For example, we can have replication factor of 3, and each block of data composing a file will be in 3 different nodes. So if a node crashes, the data is still available in two other nodes. Okay. So in this way we can ensure the efficacy of the matrix. Well, around the big data paradigm, we have these two concepts: the MapReduce and the distributed file systems. And there is, we can say, a de facto, platform, the de facto tool that is called Hadoop, that implements these MapReduce and distributed file system concepts. Okay, Hadoop is just an open source implementation that, as I told you before, Google patented an implementation, but not the concept. So we have this open source implementation about MapReduce. Okay, it is supported by Yahoo. It's based in the Google concepts. Okay, Hadoop's MapReduce is based in the following daemons. There is the task trackers daemons that are in charge of running the jobs. Okay, the map or the reduced jobs. Okay, and we have the job tracker that orchestrates these task trackers. Okay, in the sense that it sends the input splits and sends a copy of the job we are going to run to all the task trackers. And Hadoop also has the Hadoop Distributed File System (HDFS), okay, which also has a couple of nodes. We have the data node daemon that are in charge of managing data blocks. And the name node daemon that own the list of blocks per file that I was telling you before. What is interesting in Hadoop is that the name node and the job tracker usually run in the same node. I mean, we don't have nodes for the data processing and nodes for the data storage, but in Hadoop we have nodes that play the role of the name node and the job tracker, okay, and we have nodes that play the role of data node and task tracker, okay. So that's something important to have in mind, because having the analyzing process and the data in the same node improves the performance of the solution, because we don't need network operation, network transactions between processors and data managers, because everything is in the same node, so everything runs locally. And well, this accomplishes the concept about putting the processing near the data, not putting the data near the processing. Okay. Among the Hadoop ecosystem, we have the MapReduce implementation and the distributed file system, but we also have several other components in the Hadoop ecosystem. They are explained here. We have a user interface. We have several data injectors based on different kinds of data. We even have application that runs on top of Hadoop, like Pig, Hive, or OCO Mahout, that they perform different operations on top of Hadoop, are stated here in the slide. But I think we can go to explain what is Cosmos. Okay. So, well, what is Cosmos? The big question among the big data paradigm. Okay. Well, Cosmos is, first of all, Telefónica's big data platform. Okay. This means that every big data project that is held in this company, in Telefónica, is currently being run over Cosmos. Okay. This is our platform, and it's mandatory that all the big data projects run over Cosmos. We have several big data projects in Telefónica. Okay, and well, Cosmos is based on the Hadoop ecosystem. Right? We have got some pieces of the Hadoop ecosystem. We have joined them in some cases in a special way, in some cases in the de facto way. Okay, and in this way, Cosmos can be seen as a Hadoop distribution. Okay, but it's much more than a Hadoop distribution. Okay, it's cloud-based. Hadoop initially was conceived to run on community hardware, on real hardware, physical machines, but Cosmos is thought to be cloud-based. Okay, we have automatic deployment tools just to deploy Cosmos on this cloud. In this case, we have automatic deployment tools for OpenStack. Okay, we have also automatic deployment tools for other cloud that are more internal to our company. So I'm not describing them in the slide, but we have several tools for different cloud implementations. Okay. We also have an HDFS compatible SFTP injection server. This is very useful for us because we can implement injection clients for our data using this also de facto standard that is secure FTP. Okay. In the future, we will see this in the roadmap, we will have an API that is RESTful, okay, that will allow us to program the MapReduce jobs, will allow us to tell the platform which are the data that we are going to use, where to put the results, etc. So this will be an IP REST that will be deployed in the next month within the FI-WARE project and will be available. Okay. More things that Cosmos provide more than a simple Hadoop distribution. Okay, we will be in the context of the project. We will have data access protection based on OAuth. Okay, this will be explained more details in next slides. Okay, but this is something that any Hadoop distribution has nowadays. Okay, Hadoop data access protection is based on the user concept. It has been proved that this mechanism is vulnerable. I found a couple of weeks ago a link, and if you want, I can provide it. A link that is describing how this user-based mechanism for data access protection has vulnerabilities. Okay, and finally, Cosmos will be integrated with other GEs of FI-WARE, and this will improve our platform, and this will be a value add factor for Cosmos. Okay, so let's go to the Cosmos architecture. I present you how Cosmos has been designed. Okay, you have in this slide two different kinds of modules. We have the existing modules that are the white squares, and the roadmap modules that are the dark squares and that are not currently implemented. So currently, what we have is a Hadoop engine, a MapReduce engine. We also have a Hadoop distribution file system, and as I have told you, we have an SFTP injection server that allows us to inject data to our analysis cluster. Okay. As I have told you, we have automatic deployment tools that operates over all the other modules in order to automatically deploy them into a cloud. Okay. And in the future, we will have this happy rest that I have been talking to you. And also, we are going to integrate the Flume-based injection that is part of the Hadoop ecosystem, and we will integrate in the future. And we will provide an API REST for all these injectors. We will provide an API REST for accessing the Hadoop distributed file system. We will provide an API REST for the Hadoop operation, because nowadays the Hadoop operation is as simple as by logging into the machine using SSH and running the jobs by typing a command, as we will see. In the future, we provide an API REST for all this operation in order that you can integrate your application with the cluster in a FI-WARE compliant fashion, we can say. Okay. As I have told you, we are dealing with the OAuth-based authorization, just to protect the access to the data based on OAuth mechanisms. Okay, in this sense, we have to integrate with the identity manager and the access controller modules that are in the FI-WARE ecosystem. Okay, very roughly, this mechanism works as the Cosmos client provides its credentials. Cosmos client is an application that is using Cosmos, can be your applications. Okay, this application provides credentials to the identity manager. This identity manager provides an OAuth-based token, and this token is progressed within all the other operations to the different modules. So this Cosmos client tries to access the Cosmos platform, but there will be a proxy that will take this token. This token will be sent to the access controller, and this token will be used by the access controller to check the roles that the user has in the Cosmos platform, and the access controller will say the proxy, okay, this user with these roles, this user that is represented with this token, having these roles, trying to accessing this resource, this resource have access or not, and then the proxy will progress the request to the Cosmos platform. So this is the way we are foreseeing how the base authorization will be, and this is something that we have to do in the next month. Regarding the integration of Cosmos with other GEs, we have this slide. Okay, we are foreseeing to integrate with Orion, that is the implementation of the context broker GE, and we also are foreseeing to integrate with Proton, that is the complex event processing GE within the FI-WARE ecosystem. The way that we integrate is that applications can use both Orion or Cosmos. Information that is analyzed by, not information analyzed by Orion, but information that has been stored within Orion can be injected to Cosmos in order to perform high-level processing over this data, and also our results can also be published to the Orion in order to make them available to all the applications. Regarding Proton, this is a complex event processing GE, and all the data that this GE generates can also be injected to Cosmos in order to process them in a high level. Okay, and this is more or less how the integration of Cosmos platform will be with the other component of the FI-WARE ecosystem. And finally, the demo. We are going to see how currently a Cosmos distribution is like, how is the infrastructure, and how it is this environment, and we are going to see a use case and how to resolve it with Cosmos. Okay. Thus, the demo environment is the following one. Okay, we have in this case 5 nodes. Okay, we have the central node, that are the master node, and 2 slave nodes, and also an injection node. These are nodes that are running in the FI-WARE developers testbed. Okay, there will be, as you know, there will be 2 other testbeds, that will be the use cases testbed, and also the Open Innovation Lab, that will hold more instances of all the GEs. But these nodes are currently running in an internal testbed just for developers. We have a master node that will be running the main node and the job tracker. We will have two slave nodes. In a real cluster, you will have dozens, even hundreds, or in very big cases, you will have thousands of nodes. But for demonstration purposes, with a couple of nodes is enough. So we have two slave nodes, and we also have an injection node that we have used just to inject data on these data nodes. Okay. These are running, as I have told you, in this developer testbed. The nodes communicate internally by using a private network, okay, but they also expose a public interface to the internet that we will use to access, by using the access node, to access these nodes. Okay, and that's how the demo environment is conceived. Okay, the use case that I'm going to show you is the following one. Okay, let's suppose that I have a house in a town that this is a real Spanish town. Okay, this is called Malaga. Well, I'm a citizen of this town, and I'm very interested in everything that is said, that is discussed in the town hall meetings. Okay, because I'm very interested in politics, for example, and I would like to know everything that is discussed there. What's the problem? Okay, well, the problem, there's no problem. The data, this data, this information is public. It can be found in this URL. You can write this URL in your browser, and you will find this information that is real. Okay, but the problem is that just making a simple query on this URL. If we try to retrieve the information from the year 2000, we found that there are 4,598 documents. So these are a lot of documents. As a citizen, I have no time to read all the documents and try to extract information from these documents. So what can we do? Well, we can use Cosmos, okay, in the following way. We can download all the public documents into one or several files. You will see that I have downloaded this data into 3 files, okay? What we can do in order to have a better analysis is to preprocess this data, just in order to avoid certain words or certain we can call them stop words, certain words that we don't want to analyze, we don't want to appear in the results, in the analysis, okay? We can also avoid the special characters, and we are going to avoid uppercase, okay? That's going to have all the words in lowercase, okay? We can inject the resulting clean files into Hadoop distribution file system, okay? And what we are going to do is to run 2 different MapReduce jobs, okay? The first job will be a job that will be in charge of counting every word, and in this sense, this MapReduce job is the same MapReduce job that I have shown you in the presentation when I showed you how to count the words that were in a file. Okay, so we are going to perform this kind of analysis, and what we are going to obtain with this analysis is a list of sorted words. Okay. And the problem with this list is that the list will be sorted by word and not by count. So, in order to have an idea of what the town hall meetings have been discussing, well, what we can do is just to try to sort these counts and get for example, the 21st counts, and just to try to imagine what are discussing in the town hall by analyzing this top 20 words. So in order to do this, we are going to perform another MapReduce job that will perform it's called a secondary sorting on the data that provides the first MapReduce job. So in order to show you how to do this, I'm going to first of all exit the presentation. I'm going to have this terminal, okay, and this is you can see here, okay, sorry. Where is my terminal now? It's here. Okay. And this terminal, okay, represents the access node. So we are going to access the name node. Okay, we are going to access this node because there we have the binaries that we are going to run in these MapReduce jobs, and we are going to launch the jobs from the master node. Okay, we maximize the window. So we access the Cosmos name node, that is the name of this orchestrating node. So we access it, and we go to this special path. So we have here the word count operation. What we are going to do here is just to run the word count MapReduce. Okay. First of all, I would like to show you how the injected files are. We can see it by opening this window. Okay, these are the raw files that I have obtained from the public database regarding this town. Okay, these are raw files that you can see. They have special characters. Okay, they have some words that we want to avoid. Sorry, this is in Spanish, but I can translate you. This is like off, and this is like D. Okay, the terminals in English. So these are words that we want to avoid. So we are going to erase them from the file. So we have performed a pre-processing operation over this data, and this is the results. Okay, we have no special characters. Okay, we have I have also these words. Okay, no problem. I can ensure you that I have erased some words, but not this one. I don't know why, but there's no problem. Okay. And finally, well, these are the files that we have injected on the distributed file system. We can see them by performing this command. Okay, that show us which are the contents of a folder within a folder in Hadoop. Okay, so we can see that these files have been successfully injected here, and it's okay. I think we have another folder. Okay. And well, we also have raw. Okay. Well, these are the same files that we have in my local file system that I have showed you before, but these are in the distributed file system. So in this case, what we are going to run is the word count job. I'm going to run this simple script. I can show you with what this script does. Okay. What we are going to do is, well, we are going to delete previous runs of the word count job. Okay, we are going to execute this command that tells Hadoop which is the job that we are going to run. In this case, this is told by using a Java jar file. Okay, because the jobs are written in Java. Okay, this is the input of the job, and this is the output of the job. Okay, and finally, what we are going to do is just to copy all the results that are generated within the distributed file system, and we are going to copy it to my local file system. Okay, so we run this job. Okay, and we can see in the output. This takes a few seconds. Okay, so we are starting the map and reduce task. Okay, let's wait, be patient. Okay, we are progressing, and in the end, what we will have, remember, will be the list, a list, not sorted list of words, and the count for each one of these words. Okay. So we are finishing the job. It is quite slow today in my house. Yesterday it was in 5 or 7 seconds. Now it's long in a little bit more, but we are just finishing. Okay. So the MapReduce has finished, and what we have we have the results both in the distributed file system and in the local file system. I will show you the local file system results. Okay, this will be, if I remember, well, yeah, this one. Okay, so as you can see, we have a list of words. Okay, showing the occurrences, the number of occurrences regarding that word. Okay, you can see that the list is sorted by word, but not by count. And what we want is a list sorted by count and not by word, because we just want to to get the top 25 or 30 top words. Okay, so what we are going to do now is just to inject this file again to the distributed file system, and we are going to perform the secondary sorting that I have told you. Okay, in order to do that, we go to this other path, and we have here we have another script. Okay, that what does is to put in the previous MapReduce result into HDFS. Okay, we perform this secondary sorting operation. Okay, that is implemented within this in Java jar file. Okay, and this is the input. Okay, in this case will be a folder that contains the previous counts, and we provide also an output folder. And in this case, we also can provide the number of words, top words that we want to show. Okay, these results are also copied to the local file system. So I can show you how this works. So, for example, we are going to obtain the top 30 words. Okay, so we run this job, and we must wait for the result. As you can see, the jobs are not running for a long time, and this achieves the challenge regarding the velocity that I was telling you before. Sometimes, and maybe you are wondering about this, sometimes people say, okay, why don't you perform this operation just by using a simple Java program? Because if I run the same operations in a Java program, we obtain the same performance results. Okay, we can do this in a couple of seconds or even a minute. The problem is that I'm not using really big data files in this example. Okay, I'm using files that I think they are around 1 megabyte of size. But if in a real scenario we use files that are about gigabytes, and we have thousands of these kind of files, a simple program cannot deal with this. Okay, so we need this. We need the distributed processing capabilities that provide Cosmos or Hadoop. So in this case, we have finished this secondary sorting, and I'm able to show you the results. And the results are in this file, I think. So yeah. So these are the top 30 words that appear in these public town hall meetings. Okay, and I can translate you the words. Okay, this is in English public. Okay, this is very interesting. The second word in Spanish, multa. In English is fine. Okay, when you are punished by paying a certain amount of money, because, for example, you have gone very fast with your car. Okay, you are fine. Okay, but in Spanish we say multa, and it's very interesting that this is the second word with more occurrences in this discussion about the town hall meetings of this town. Okay, so this is very interesting. More interesting words. Well, okay, these are technical words that appear in all the public documents of such meetings. This is about the resolutions, orders, laws that are being discussed. Okay, this is very similar in English. I think this is urbanism. Okay, and this is a name. This is a Spanish name that is Francisco. And you can see here Francisco, and also you can see here, I think, Jose, that are Spanish names, and Francisco and Jose are the two names that have the mayor of the town hall. I think he's called Francisco Jose. The reason, because we have 100 occurrences of Francisco and less occurrences of Jose, is because I think sometimes they will call him Francisco Jose, and other times the mayor will be told about only Francisco. Okay, And we also I think we also have an interesting word. Okay, yes. This is bebidas in español, in Spanish, sorry. In English, this is drinks. Okay, so it's also very interesting that in the town hall meetings they talk about drinks. I don't know why. I suppose that they talk about drinks in the sense of how to forbid the people drink in the street, or how to regulate how people drink in the local parties of the town, or and so on. I think. Okay, and this word relates about cleaning. Okay, limpieza in Spanish. And that's all. I think this is okay. This is a very simple way and not very sophisticated way to know what the town hall meetings discussion are about. But it's a way. Okay, we will program a more complex program in order to make a more deeper analysis. We could perform correlation analysis. We could perform some other analysis, even in top of Cosmos Hadoop, using machine learning algorithms, etc. But I think these examples summarize in a simple way how we can use MapReduce techniques in order to get this kind of information. And I think that's all from my side. I don't know if you have any question. You have been very silent all along the presentation. So do you have any question? Something that you want to know about Cosmos, about the roadmap, how it is implemented?
Yes, part of this is from NDUA. For example, can you hear me?
Yeah. Tell me.
Yeah. Okay, I have a question about the roadmap. Actually, can you go back to slide 16,
Yeah.
I think?
Yep. I can go to the roadmap slide. Wait a moment. I think this one or the test version of the roadmap. I think you are talking about this one.
About 16, about the Cosmos architecture, actually.
This one.
Okay, yeah. So I just want to know what is available right now in release 2.0.
Okay, in the current release, we have available the boxes that are white, the white boxes. Okay, we have the MapReduce engine, we have the HDFS, we have the injection server, and we have automatic deployment tools for deploying the SFTP injection server, the MapReduce nodes, and the distribute file node. Okay. So this is what we currently have in this release. Regarding the automatic deployment, okay, the scripts. I don't know if you know. In the context of FI-WARE, we are using automatic deployment mechanism that is called Chef. Okay, this is by Opscope, sorry, the Opscope company, and what we have is a set of scripts written in Chef, that is an extension of the Ruby language. And what we have is this scripts that can be accessed by the FI-WARE portal. And in the Open Innovation Lab, for example, you will be able to deploy a Cosmos cluster by using we can say just a single button in the portal that will say, okay, automatically deploy a Cosmos cluster. And in a transparent way, these scripts will deploy the Hadoop MapReduce engine, the distributed file system, the injection server, and so on.
So regarding the API and the Cosmos client, when are they going to be available? If you know more or less.
We don't know. We know that it's in the roadmap, okay, but I don't know if it will be in the next release. I don't know if it will be in 3.1 or 3.2, but for sure it will be in the worst case in the last release of the release 3. Okay. But think that I think it's not as important the Cosmos client as the RESTful API, because having the RESTful API you can develop your own client, because the Cosmos client is just a tool for programming jobs and telling Hadoop which are the input files where you expect to have the results. But it's just a client, of course, that you can use it, okay? But I think it's more interesting to have the API REST will be, because you can develop your own client and you can do whatever you want with the operation that we are going to expose in this API.
Okay, and last thing is regarding the Flume-based injection engine. This is about real-time data, right?
Sorry, can you repeat, please?
So I guess we use the Flume for real-time data injection.
Yeah, for real-time data, yeah, because
so this is not available.
No, not available yet. I think this thing will be one of the modules that will be available first, because I think people that is working on Cosmos will find very easy to integrate the human modules that are available in the Hadoop ecosystem, and they will find very easy to integrate it with the current release, because I think it's as simple, as simple as integrating the existing module and having all the interfaces working. I think it will be really very soon.
Okay, and one final question from my side, not to have more time for me. So, okay, I'm not, let's say, a big data expert, but I did not understand why you did twice the MapReduce jobs in the demo. Is that for the demo? I mean, can we sort the initial file plain and simple? Do we need the MapReduce technique for sorting?
Yeah. I have performed 2 different MapReduce in order to show you how we can a simple word count operation can do, and how a secondary sorting operation can do. But of course, you can find in the internet examples of Hadoop or MapReduce jobs that perform the secondary sorting in just a single MapReduce job. Yeah, of course, you can do it.
Okay.
Yeah, it's more complex, and you have to deal with more. How to say? You have to have a deep understanding of how the MapReduce concept works. But it is possible, of course. You can do everything in a single job.
Thank you very much.
Okay, thank you. Any more questions? Okay, it seems that everything is clear enough. So I think we can finish this webinar. Thank you everyone for attending to this webinar. And if you have any questions, you can write me at this email address, frb@tid.es. Okay, so write me every question you have, and I'll answer it. Okay, so thank you. That's all. Bye.
Okay, thank you. Bye.
Bye.
Bye.